Hi, this is Unit 2 of this video lesson series, and we're going to talk about force and translational motion. So the most important takeaway in here is that we can look at a system as if it is just its center of mass. So an object can be simplified into a singular center, so the single dot has all the mass, all the velocity, all the acceleration, etc. If you want a more in-depth description, you can read the exam description, but because this is a brief video, I'm not going to talk about that. So now that we know what this is, we should probably find a way to get it, right? So the most general equation for the center of mass is this one. I'm not going to read it out loud because it's so complicated. R is any variable in which the mass is distributed in respect to. dm is the infinitesimal mass. I feel like it would really help you to know how exactly we got here. So the easiest way to think about the center of mass is we're going to get the average location of the mass in respect to like a certain variable, as I mentioned. So I hope this makes sense because this is basically the premise of how we got here. As we can see, we multiply all the masses with their location and we divide it by the mass. And then intuitively, you would get the average location of the masses, right? If you're finding the average of something, you would add it all up and then divide it by the number of things you added all up, right? We're doing the same thing with location here. And if we did that like a lot of times and we're adding infinitesimal tiny masses, it would become an integral eventually, right? Because we learn calculus and everything. So that's what we get. And as we know, if we add all of the tiny masses up, you would just get the whole mass, right? So you take that out and then eventually you just get this equation. One quick thing to note is that we're going to use this lambda thing a lot, and basically what it is linear density or just density. Sometimes it's an equation, sometimes it's a number. And basically what it does is that they make it possible that we can make dm into something in respect to r. We can do this because the total mass over total r is equal to dm over dr. It's because we assume that the density is going to be the same no matter where we go. But this kind of changes when we're talking about non-uniform solid objects. But then we can basically just use an equation. So it's basically the same thing. And therefore, you can get this one, and then you plug it in, and then you get this. And now you can integrate it because now everything is in respect to r. If we remember, if we're using point masses within a linear axis, then we can basically use the average equation like that. So if we, for instance, have this axis and then there's these like different point masses, then we can just do that where we get m1 r1 plus m3 r3 plus m2 r2, and then we divide it up by the masses, and then we would get the average location of the mass. So for non-uniform density solid objects, unlike the point masses, is that we have to use the integration equation that we used before. This isn't that hard for a uniform density solid object. Basically what you do is that you pretend that the linear density or whatever density is a constant, and then you just take it all out, and then you integrate the part inside it, and then you have to use this equation that works because we know that it's a uniform density one, so it's not an equation, and you just plug it into the mass, and then that will get rid of the lambdas, and then you will get this. Where it does get kind of confusing is when it's non-uniform density. So the reason why is because usually the lambda has a weird shape like this. I probably should use the example in the notes. Like that, where it's lambda 0 multiplied by some kind of equation in respect to, in here it's x-axis, x-axis, so I'm just going to say that. But initially what you do is the same. You plug in that one for the lambda, you get the lambda 0, which is technically also a constant, so you take it out. You integrate that part, which you did the same in the initial example. But when it does differ is that we want to get rid of these. We want to get rid of these and turn it into a L. And how we do that is that we basically take an integration again. So you get the lambda in as we would usually do to get the mass. You multiply by dx, and then you take the lambda 0 and then blah 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 blah. What you get is this in the end, and then you plug it in into that, and then that would get rid of the lambda 0, and then you would get a clean equation. If you still have lambda 0 or like other weird stuff lingering around after this, you probably did do something wrong and you should check yourself.